Everything you see, your chair, your lunch, the air, even you, is made of atoms. These are the universe's ultimate Lego bricks, building everything from stars to grains of sand. Atoms are the fundamental building blocks of all matter. Each atom has a nucleus at its center, made of protons and neutrons with electrons whizzing around it, like a tiny solar system. The number of protons, neutrons, and electrons determines what kind of atom it is: hydrogen, oxygen, carbon, and so on. The way atoms connect, called chemical bonds, creates all the materials we know. Understanding atoms is the key to understanding our universe. For centuries, atoms were just an idea, too small to see even with the best microscopes. Scientists built theories and models, but it was like describing someone by their shadow. The dream was to see a single atom, the building block of our world, with our own eyes. That dream finally came true in a very special way. Atoms are about 1/10,000,000th of a millimeter wide, so small you could fit 1,000,000 across a human hair. To put that in perspective, if a single atom were the size of a marble, a human hair would be as wide as a football field. Their minuscule size makes them far beyond the reach of our eyes or even most scientific instruments. They're much smaller than the wavelength of visible light, so light waves just pass over them. Light, which we use to see everything around us, simply can't bounce off atoms in a way that would let us see them directly. That's why even the most powerful light microscopes can't see a single atom. No matter how much you magnify, atoms remain invisible to traditional optical tools. Scientists had to invent new tools, like the scanning tunneling microscope, which feels atoms instead of seeing them. These devices use incredibly fine tips to detect the presence of atoms by measuring tiny electrical currents. Another challenge: atoms are always moving, jiggling at incredible speeds. They vibrate and dart around, even at temperatures close to absolute zero. Taking a clear photo of an atom is like trying to photograph a hummingbird's wings in flight. The motion blurs any image you try to capture, making it nearly impossible to get a sharp picture. To see an atom, you have to trap it and make it hold still. An enormous technical challenge. Scientists use electromagnetic fields and lasers to pin atoms in place, freezing their motion for just long enough to observe them. For centuries, seeing a single atom was considered impossible. The idea of actually observing one was more a dream than a goal. You could see their effects or groups of atoms, but never just one. Scientists could infer their existence from experiments, but direct observation was out of reach. Capturing a photo of a lone atom glowing in space seemed like science fiction. It was the kind of thing you'd expect to see in a futuristic movie, not a real laboratory. To do it, you'd need to trap a single atom and make it shine bright enough for a camera. This requires not only advanced technology, but also a deep understanding of atomic physics and optics. It was a challenge that needed a brilliant idea and a lot of patience. Years of trial and error, creative problem solving, and persistence were essential. Until one day, someone made it happen. The impossible became possible, and for the first time, we could finally see the building blocks of our universe. The breakthrough came from David Nadlinger, a graduate student at Oxford, whose passion for physics and curiosity about the universe drove him to explore the unknown. In 2017, while working late in his lab, David found himself pondering a question that had fascinated scientists for decades. Could he actually photograph a single atom with a regular camera, something that had never been done before? His experiment was already trapping single atoms using carefully aligned lasers, a process that required immense precision and patience. He decided to take things a step further. David set up his equipment to trap just one strontium atom, then pointed a digital camera at the heart of the machine, using a long exposure to try and capture the impossible. In the quiet, darkened lab, he took the shot and waited, heart pounding, hoping that the camera would reveal what the naked eye could not see. When the image finally appeared, there it was, a tiny pale blue dot suspended between metal electrodes. It was a single atom, glowing softly, visible to the world for the very first time. David had achieved what many thought was impossible. He had captured a photograph of a single atom, something that had only existed in theory or as an artist's impression until then. His photo, Single Atom in an Ion Trap, quickly became famous, inspiring scientists and the public alike, and went on to win a major science photography prize, cementing its place in history. What's truly inspiring is that this wasn't the result of a massive, expensive project. It was the product of a curious scientist daring to ask, what if? And following that question wherever it led. Sometimes the biggest breakthroughs in science come not from grand plans, but from a simple question, and the courage to try something new, even if it seems impossible. Thanks to David's idea and determination, the world was able to see, with its own eyes, the building block of our universe, a single atom captured in a photograph. It was a beautiful, profound moment that reminded us all of the wonder and mystery still waiting to be discovered in the world around us. And it all started with curiosity, a simple question, a bold idea, and the determination to see it through. Photographing a single atom takes a high-tech setup, a kind of microscopic prism. First, you turn a neutral atom into an ion by knocking off an electron, giving it a charge. This lets you control it with the electric fields. The ion trap uses metal electrodes to create a force field, holding the charged atom perfectly still. The trap is inside an ultra-high vacuum chamber, almost a perfect empty space, so nothing bumps the atom out of place. The vacuum is so good, the atom can stay trapped for hours. With the atom trapped and isolated, David used a regular DSLR camera with a special lens set for a long exposure. The camera looked through a window into the vacuum chamber, focused on the tiny gap between electrodes. The whole system, ion trap, vacuum, lasers and camera, had to work in perfect harmony. It was a symphony of technology, all to capture the light from a single atom. The result, a visible dot of light, proof of a single atom's existence. Science at its most precise. Trapping the atom is only half the battle. Once you've managed to hold a single atom in place, the next challenge is to control its energy and motion with incredible precision. You also need to make it shine, to coax it into revealing its secrets by interacting with light in just the right way. Enter laser cooling, a revolutionary technique where scientists use finely tuned lasers to slow the atom's motion, draining away its heat and making it incredibly cold, just a fraction of a degree above absolute zero, the coldest temperature possible in the universe. Lasers of a very specific color or wavelength are aimed at the atom from all directions, creating a perfectly balanced trap of light. The atom absorbs photons from the laser beams, each one giving it a tiny push in the opposite direction of its motion, gradually slowing it down. This process keeps the atom stable and nearly motionless in the trap, allowing scientists to study it in exquisite detail. Every time the atom absorbs a photon, it jumps to a higher energy state, an excited state, then almost instantly releases that energy as a new photon. This process is called fluorescence, and it's the key to making the atom visible. The atom glows, emitting tiny flashes of light in all directions, like a microscopic beacon in the darkness of the lab. The blue laser used in this experiment was tuned perfectly to the strontium ion's unique energy levels, making it emit blue photons hundreds of thousands of times per second, far too fast for the human eye to see, but easily detected by sensitive cameras. Even though the light from a single atom is incredibly faint, almost ghostly, a long camera exposure can collect enough of these photons over time to make the atom visible as a tiny glowing dot. The same lasers that cool the atom also make it glow for the camera, serving a dual purpose in this delicate experiment. It's a stunning use of light and quantum physics to reveal the building blocks of matter, allowing us to see the invisible. Without laser cooling, the atom would move too quickly to be seen, and the photo would be impossible. This is quantum physics in action, turning the abstract world of atoms into something we can actually observe and study. Why strontium? Its electron structure makes it ideal for laser control. Strontium's electrons allow for a cycling transition. It can absorb and emit photons millions of times per second without going dark. This makes it a bright, reliable source of light for the camera. The lasers needed for strontium are easy to produce and very stable. Strontium is also a top candidate for quantum computers and atomic clocks. Its quantum properties make it perfect for storing information as a qubit. So, controlling a single strontium atom isn't just about a cool photo, it's practice for building the technology of the future. The atom and the tools are a perfect match. Nardlinger's photo is more than a curiosity, it's a symbol of our control over the quantum world. Quantum computers use qubits, which can be 0, 1, or both at once thanks to superposition. A single trapped ion, like strontium, is a leading way to create a stable qubit. Scientists use lasers to put the atom into superposition, representing zeros and ones with different energy levels. The photo proves we can isolate and control these qubits. To build a quantum computer, you need to control many qubits at once. Seeing the atom confirms the experiment is working and inspires confidence in quantum technology. What once sounded like science fiction is now real. Each trapped ion is a step towards solving problems no supercomputer can touch. Seeing and controlling a single atom opens up a world of possibilities. Single atoms can be used as ultra-precise sensors, detecting tiny changes in gravity or magnetic fields. The most accurate clocks, atomic clocks, are moving toward using single trapped ions for even greater precision. This could revolutionize GPS, finance, and deep space communication. In medicine and materials science, manipulating atoms could lead to custom drugs and new materials. We're moving from working with bulk materials to building with individual atoms. It's a profound shift, like going from boulders to bricks. The precision and potential are almost limitless. This tiny dot of light is a beacon, showing the path to a future of incredible technology. The age of atomic control has begun. David Nadlinger's photo is a landmark in science. For millennia, atoms were just an idea. Now anyone can see one. The image connects us to the universe's fundamental reality. It's a powerful tool for education and inspiration, sparking curiosity in future scientists. The story shows that big discoveries can come from simple questions and creative thinking. This single dot of light marks a new era in our ability to manipulate the world at its smallest scale. It's a hello world moment for quantum technology. Looking at that pale blue dot, we see the same building blocks as stars and ourselves. The photo is a celebration of human ingenuity and our quest to explore the unknown. Even the smallest things can hold the universe's biggest secrets.